So, hello everyone. The topic that we are going to discuss today is the P block elements, and we are continuing with group 16 elements. We have already completed group 13, group 14, and group 15. If you haven't gone through the video yet, you can watch the video and listen to the audio. So, without wasting any time, let's start group 16 elements. Oxygen, sulfur, selenium, tellurium, polonium, and livermorium constitute group 16 of the periodic table. The mnemonic for this that is I have made is oxygen O, sulfur Sir, selenium Se, tellurium Te, and PO Po, and for Li it is Li. So O Sir Se T Po, O Sir Se T Po. So this is the mnemonic. Let's continue. This is sometimes known as group of chalcogens. The name is derived from the Greek word for brass and points to the association of sulfur and it congeners with copper. Most copper minerals contain either oxygen or sulfur and frequently the other members of the group. Occurrence. Oxygen is the most abundant of all the elements on the earth. Oxygen forms about 46.6% by mass of the earth's crust. Dry air contains 20.946% of oxygen by volume. However, the abundance of sulfur in the earth's crust is only 0.03 to 0.1%. Combined sulfur exists primarily as sulfates such as gypsum CaSO4.2H2O, Epsom salt MgSO4.7H2O, barite BaSO4, and sulfides such as galena PbS, zinc blende ZnS, copper pyrites CuFeS2. Traces of sulfur such as traces of sulfur occurs as hydrogen sulfides in volcanoes. Organic materials such as eggs, proteins, garlic, onion, mustard, hair, and wool contain sulfur. Selenium and tellurium are also found as metal selenides and tellurides in sulfide ores. Polonium occur in nature as a decay product of thorium and uranium minerals. Livermorium is a synthetic radioactive element. Its symbol is Lv, atomic number 116, atomic mass 292, and electronic configuration Rn 5f14, 6d10, 7s2, 7p4. It has been produced only in a very small amount and has a very short half-life, only a small fraction of 1 second. This limits the study of properties of Lv. Here, except for livermorium, important atomic and physical properties of other elements of group 16 along with their electronic configuration are given in table 7.6. Some of the atomic, physical, and chemical properties and their trends are discussed below. So, here you can see properties like atomic number, mass number, electronic configuration, covalent radius, say TPO is given, so you can go through it. Electronic configuration. The elements of group 16 have 6 electrons in the outermost shell and have Ns2Np4 general electronic configuration. Due to increase in the number of shells, atomic and ionic radii increases from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. Ionization enthalpy. Ionization enthalpy decreases down the group. It is due to increase in size. However, the element of this group have lower ionization enthalpy values compared to those of group 15 in the corresponding period. This is due to the fact that group 15 elements have extra stable half-filled p orbitals electronic configuration. Electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. Electronegativity. Next to fluorine, oxygen has the highest electronegativity value amongst the element. Within the group, electronegativity decreases with an increase in atomic number. This implies that the metallic character increases from oxygen to polonium. Elements of group 16 generally show lower value of first ionization enthalpy compared to the corresponding periods of group 15. Why? The answer is very easy. Due to extra stable half-filled p orbitals, electronic configuration of group 15, larger amount of energy is required to remove electrons as compared to group 16 elements. Physical properties. Some of the physical properties of group 16 elements are given in the table 7.6. Oxygen and sulfur are nonmetals. Selenium and tellurium metalloids, whereas polonium is a metal. Polonium is radioactive and is short-lived. Half-life 13.8. All these elements exhibit allotropy. The melting and boiling point increase with an increase in atomic number down the group. The large difference between melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as a diatomic molecule, whereas sulfur exists as a polyatomic molecule S8. Chemical properties, oxidation states and trends in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, except in case of OF2 where its oxidation state is +2. Other elements of the group exhibit +2, +4, +6 oxidation state, but +4 and +6 are more common. Sulfur, selenium and tellurium usually show +4 oxidation state in their compounds with oxygen and +6 with fluorine. The stability of +6 oxidation state decreases down the group and stability of +4 oxidation state increases. Inert pair effect. Bonding in +4 and +6 oxidation state is primarily covalent. Anomalous behavior of oxygen. The anomalous behavior of oxygen, like other members of P block present in the second period, is due to its small size and high electronegativity. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in water, which is not found in H2S. The absence of d orbital in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalency exceeds 4. Reactivity with hydrogen. All the elements of group 16 form hydrides of the type H2E, where E is the element of group 16 element, that is O sir se tipo. Some properties of hydrides are given in table 7.7. Their acidic character increases from water to H2TE. The increase in acidic character can be explained in terms of decrease in bond enthalpy for the dissociation of hydrogen E bond down the group. Owing to decrease in enthalpy for the dissociation of He bond down the group, the thermal stability of hydrides also decreases from H2O to H2PO. All the hydrides except water possesses reducing property, and this character increases from H2S to H2TE. So you can look at the properties of the hydride which is shown in the table. You can compare the melting point, boiling point, then the bond distance between hydrogen and the element of group 16. Reactivity with oxygen. All these elements form oxide of EO2 and EO3 type, where E is sulfur, selenium, tellurium, or polonium. Ozone O3 and sulfur dioxide SO2 are the gases, while selenium dioxide is solid. Reducing property of dioxide decreases from SO2 to TeO2. SO2 is reducing while TeO2 is an oxidizing agent. Besides, EO2 type sulfur, selenium, and tellurium also form EO3 type oxides. SO3, SeO3, TeO3. Both types of oxides are acidic in nature. Reactivity towards the halogens. Elements of group 16 form a large number of halides of the type EX6, EX4, and EX2, where E is an element of the group and X is a halogen. The stability of halide decreases in the order F minus, which is greater, then Cl minus, then Br minus, and then I minus. Amongst hexahalides, hexafluorides are the only stable halides. All hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable for steric reasons. Amongst tetrafluorides, SF4 is a gas, SeF4 a liquid, and TeF4 a solid. These fluorides have sp3d hybridization and thus have trigonal bipyramidal structures in which one of the equatorial position is occupied by a lone pair of electrons. This geometry is also regarded as seesaw geometry. All elements except oxygen form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are dimeric in nature. Examples are S2F2, S2Cl2, S2Br2, SeCl2, and Se2Br2. These dimeric halides undergo disproportionation as given below. डिस्प्रपोर्शनेशन में क्या होगा, SeCl2 है वो ब्रेक हो जाएगा एंड क्या हो जाएगा, SeCl4 बन जाएगा प्लस 3 सेलेनियम इज रिलीज्ड. H2S is less acidic than H2TE. Why? Due to decrease in bond between EH, dissociation enthalpy down the group, acidic character increases. Dioxygen. Preparation. Dioxygen can be obtained in laboratory by the following ways. First, by heating oxygen containing salt such as chlorates, nitrates, and permanganates. KClO3, when heated in presence of MnO2, it will give potassium chloride and oxygen is released. So, dioxygen ka preparation. Second, by thermal decomposition of the oxides of metals low in the electrochemical series and higher oxides of some metals. तो अगर हम सिल्वर ले रहे हैं, मर्क्यूरी ले रहे हैं एंड लेड ले रहे हैं, उनके कोई भी ऑक्साइड्स ले रहे हैं तो फॉर श्योर हमें क्या मिल जाएगा, डाइऑक्सीजन मिल जाएगा. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. H2O2 कैटलिस्ट के प्रेजेंस में क्या दे देगा, पानी प्लस ऑक्सीजन गैस रिलीज हो जाएगा. On large scale, it can be prepared from water or air. Electrolysis of water leads to the release of hydrogen at the cathode and oxygen at the anode. An important question over here कि कैथोड पे क्या रिलीज हो रहा है, एनोड पे क्या रिलीज हो रहा है. एंड लार्ज स्केल प्रोडक्शन में हम लोग क्या करते हैं, इलेक्ट्रोलिसिस ऑफ वाटर करते हैं फॉर प्रिपरेशन ऑफ डाई ऑक्सीजन. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. Properties: dioxygen is a colorless and odorless gas. Its solubility in water is to the extent of 3.02 cm cube in 100 cm cube water at 293 Kelvin, which is just sufficient for the vital support of marine and aquatic life. It liquefies at 90 Kelvin and for the vital support of marine it liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen atom has three stable isotopes, O16, O17 and O18. Molecular oxygen, O2, is unique in being paramagnetic in spite of having even number of electrons. You can see in the class 11 chemistry book, unit 4. Dioxygen directly reacts with nearly all metals and non-metals except some metals like gold and platinum and some noble gases. Its combination with other elements is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required as bond dissociation enthalpy of oxygen-oxygen double bond is high, 493.4 kilojoule per mole. Some of the reactions of dioxygen with metals, non-metals and other compounds are given below. तो आप देख रहे हो कैल्शियम जब ऑक्सीजन के साथ रिएक्ट करेगा तो कैल्शियम ऑक्साइड बन गया. एल्यूमिनियम जब ऑक्सीजन के साथ रिएक्ट करेगा तो एल्यूमिना Al2O3 बन गया. फॉस्फोरस जब ऑक्सीजन के साथ रिएक्ट करेगा तो P4O10 बन गया. कार्बन जब ऑक्सीजन के साथ रिएक्ट करेगा तो कार्बन डाइऑक्साइड बन गया. जिंक सल्फाइड प्लस ऑक्सीजन रिएक्ट करेंगे तो जिंक ऑक्साइड एंड SO2 सल्फर डाइऑक्साइड बन जाएगा. मीथेन अगर ऑक्सीजन के साथ रिएक्ट कर जाएगा तो कार्बन डाइऑक्साइड प्लस वाटर रिलीज हो जाएगा. सम कंपाउंड्स आर कैटालिटिकली ऑक्सीडाइज्ड. फॉर एग्जांपल, सल्फर डाइऑक्साइड प्लस ऑक्सीजन इन द प्रेजेंस ऑफ V2O5 दैट इज वेनेडियम पेंटॉक्साइड, वो क्या हो जाएगा, SO3 सल्फर ट्राइऑक्साइड विल गेट फॉर्म्ड. HCl plus oxygen in presence of copper chloride will give Cl2, that is chlorine, plus water. Uses: in addition to its importance in normal respiration and combustion processes, oxygen is used in oxyacetylene welding, in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high altitude flying, and in mountaineering. The combustion of fuels, example hydrogens in liquid oxygen, provides tremendous thrust in rockets. Simple oxides. A binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with most of the elements of the periodic table to form oxides. In many cases, one element forms two or more oxides. The oxides vary widely in their nature and properties. Oxides can be simple, example magnesium oxide, that is MgO, Al2O3, or mixed, Pb3O4, Fe3O4. Simple oxides can be classified on the basis of their acidic, basic, or amphoteric character. An oxide that combines with water to give an acid is termed acidic oxide. Example, SO2, Cl2O7, carbon dioxide, N2O5. For example, SO2 combines with water to give H2SO3, an acid. Sulfur dioxide, SO2 plus water will react to give H2SO3. As a general rule, only non-metal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character. Example, Mn2O7, CrO3, B2O5, etc. The oxides which give a base with water are known as basic oxides. Example, Na2O, calcium oxide, barium oxide. For example, calcium oxide combines with water to give calcium hydroxide. और ये calcium hydroxide क्या है? एक base है. ठीक है. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acid as well as alkalis. For example, Al2O3 reacts with acid as well as alkalis. So here you can see the reaction of Al2O3 with HCl, that is acid. Also Al2O3 is reacting with NaOH, that is a base. You can see what is the complex formation that is occurring. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxide. Examples of neutral oxides are carbon monoxide, CO, NO and N2O. Again ये भी क्वेश्चन इंपॉर्टेंट होता है, पूछ लेते हैं न्यूट्रल ऑक्साइड्स कौन से हैं. तो CO, NO and N2O. Ozone. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in the atmosphere at sea level. At a height of about 20 kilometers, it is formed from the atmospheric oxygen in the presence of sunlight. This ozone layer protects the Earth's surface from an excessive concentration of ultraviolet UV radiations. Preparation. When a slow, dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone 10% occurs. The product is known as ozonized oxygen. 3O2 gives 2O3. Since the formation of ozone from oxygen is an endothermic process, it requires heat, that is 142 kilojoule per mole. It is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. If concentration of ozone is greater than 10% are required, a battery of ozonizers can be used and pure ozone, boiling point 101.1 Kelvin, can be condensed in a vessel surrounded by liquid oxygen. Properties. Pure ozone is the pale blue gas, dark blue liquid and a violet black solid. Ozone has a characteristic smell and in small concentrations it is harmless. However, if the concentration rises above 100 parts per million, breathing becomes uncomfortable, resulting in headache and nausea. Ozone is thermodynamically unstable with respect to oxygen since its decomposition into oxygen results in liberation of heat. Delta H is negative and increase in entropy, that is delta S is positive. These two effects reinforce each other, resulting in a large negative Gibbs energy change delta G for its conversion into oxygen. It is not really surprising, therefore, high concentration of ozone can be dangerously explosive. Due to ease with which it liberates atom of nascent oxygen, O3 gives oxygen, O2 plus nascent oxygen. It acts as a powerful oxidizing agent. For example, it oxidizes lead sulfide to lead sulfate and iodide ions to iodine. You can look at the reaction that is shown in the screen of your textbook. When ozone reacts with an excess of potassium iodide solution buffered with a borate buffer pH 9.2, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating O3 gas. Experiments have shown that nitrogen oxides, particularly nitrogen monoxide, combine very rapidly with ozone, and there is thus the possibility that nitrogen oxides emitted from the exhaust system of supersonic jet aeroplanes might be slowly depleting the concentration of the ozone layer in the upper atmosphere. NO plus ozone will give NO2 plus O2. Another threat to this ozone layer is probably posed by the use of freons, which are used in aerosol sprays and as refrigerants. The two oxygen oxygen bond lengths in the ozone molecule are identical, 128 picometer, and the molecule is angular as expected with a bond angle of about 117 degree. It is a resonance hybrid of two main forms. Uses: it is used as germicide, disinfectant, and for sterilizing water. It is used for bleaching oils, ivory, flour, starch, etc. It acts as an oxidizing agent in the manufacture of potassium permanganate. Sulfur. Allotropic forms. Sulfur forms numerous allotropes, of which the yellow rhombic alpha sulfur and monoclinic beta sulfur forms are the most important. The stable form at room temperature is rhombic sulfur, which transforms to monoclinic sulfur when heated above 369 Kelvin. Rhombic sulfur, alpha sulfur. This allotrope is yellow in color, melting point 385.8 Kelvin, and specific gravity 2.06. Rhombic sulfur crystals are formed on evaporating the solution of roll sulfur in CS2. It is insoluble in water but dissolves to some extent in benzene, alcohol, and ether. It is readily soluble in CS2. Monoclinic sulfur, beta sulfur. Its melting point is 393 Kelvin and specific gravity 1.98. It is soluble in carbon sulfide. This form of sulfur is prepared by melting rhombic sulfur in a dish and cooling till crust is formed. Two holes are made in the crust and the remaining liquid poured out. On removing the crust, colorless needle-shaped crystals of beta sulfur are formed. It is stable above 369 Kelvin and transforms into alpha sulfur below it. Conversely, alpha sulfur is stable and is stable between 369 Kelvin and transforms into beta sulfur above this. At 369 Kelvin, both the forms are stable. This temperature is called transition temperature. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structures. The S8 ring molecules are packed. The S8 ring in both the forms is puckered and has a crown shape. The molecular dimensions are given in figure 7.5a. Several other modifications of sulfur containing 6 to 20 sulfur atoms per ring have been synthesized in the last 2 decades. In the cyclo S6, the ring adopts the chair form and the molecular dimensions are as shown in figure 7.5. At elevated temperatures, S2 is the dominant species and is paramagnetic like O2. Example 7.12. Which form of sulfur shows paramagnetic behavior? In vapor state, sulfur partly exists as S2 molecule, which has two unpaired electrons in the anti-bonding pi star orbitals like O2 and hence exhibits paramagnetism. Sulfur dioxide. Preparation. Sulfur dioxide is formed together with a little 6 to 8% sulfur trioxide when sulfur is burnt in air or oxygen. So sulfur reacts with oxygen to give sulfur dioxide. In laboratory, it is readily generated by treating a sulfite with dilute sulfuric acid. So SO3 2 minus plus 2H plus will give water and sulfur dioxide. Industrially, it is produced as a byproduct of the roasting of sulfide ores. FeS2 plus oxygen will give Fe2O3 plus SO2. The gas after drying is liquefied under pressure and stored in steel cylinders. Properties: sulfur dioxide is the colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmospheres and boil at 263 Kelvin. Sulfur dioxide, when passed through water, forms a solution of sulfurous acid, SO2 plus water, which gives H2SO3. It reacts readily with sodium hydroxide solution, forming sodium sulfite, which then reacts with more sulfur dioxide to form sodium hydrogen sulfite. So NaOH reacts with SO2 sulfur dioxide to give Na2SO3 sodium sulfite. यही सोडियम सल्फाइड पानी और वापस से सल्फर डाइऑक्साइड से रिएक्ट करके क्या बनाता है सोडियम हाइड्रोजन सल्फाइड NaHSO3. In its reaction with water and alkalis, the behavior of sulfur dioxide is very similar to that of carbon dioxide. Sulfur dioxide reacts with chlorine in the presence of charcoal, which act as a catalyst to give sulfuryl chloride, SO2Cl2. It is oxidized to sulfur trioxide by oxygen in the presence of vanadium 5 oxide catalyst. SO2 reacts with chlorine to give SO2Cl2. SO2 reacts with oxygen in presence of vanadium pentoxide to give SO3, that is sulfur trioxide. When moist sulfur dioxide behaves as a reducing agent, for example, it converts iron 3 ions to iron 2 ions, मतलब Fe3 plus को वो Fe2 plus कर देता है, and decolorizes acidified potassium permanganate solution. The latter reaction is a convenient test for the gas. तो आप यहाँ पर देख सकते हो, in the reaction it is shown Fe3 is getting converted to Fe2 plus, ठीक है, and Mn is also getting converted into Mn2 plus. The molecule of SO2 is angular. It is a resonance hybrid of two canonical forms. Uses: sulfur dioxide is used in refining petroleum and sugar, in bleaching wool and silk, and as an anti-chlor, disinfectant and preservative. Sulfuric acid, sodium hydrogen sulfide and calcium hydrogen sulfide, industrial chemicals, are manufactured from sulfur dioxide. Liquid SO2 is used as a solvent to dissolve a number of organic and inorganic chemicals. Oxoacids of sulfur. Sulfur forms a number of oxoacids such as H2SO3, H2S2O3, H2S2O4, H2S2O5, H2SXO6, where X can be 2 also and it can be 2 to 5. Okay, H2SO4, H2S2O7, H2SO5, H2S2O8. Some of these acids are unstable and cannot be isolated. They are known in aqueous solution or in the form of their salts. Structures of some important oxoacids are shown in the figure. So here you can see the structures of oxoacid, that is sulfurous acid, sulfuric acid, peroxodisulfuric acid, pyrosulfuric acid, that is oleum. The structures and the names and the molecular formula of the acid becomes very important. Sulfuric acid. Manufacture. Sulfuric acid is one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by the contact process, which involves 3 steps. First, burning of sulfur or sulfide ores in air to generate SO2. Second, conversion of SO2 to SO3 by the reaction with oxygen in the presence of catalyst V2O5. And third, absorption of SO3 in H2SO4 to give oleum, that is H2S2O7. A flow diagram for the manufacture of sulfuric acid is shown in the figure. The SO2 produced is purified by removing dust and other impurities such as arsenic compounds. The key step in the manufacture of H2SO4 is the catalytic oxidation of SO2 with O2 to give SO3 in the presence of catalyst V2O5. SO2 plus O2 catalyst V2O5 क्या मिल जाएगा SO3, and it is an exothermic reaction. 196.6 kilojoule per mole is the heat that is removed. The reaction is exothermic, reversible, and the forward reaction leads to decrease in volume. Therefore, low temperature and high pressure are the favorable condition for the maximum yield. But the temperature should not be very low. Otherwise, rate of reaction will be slow. In practice, the plant is operated at a pressure of 2 bar and a temperature of 720 Kelvin. The SO3 gas from the catalytic converter is absorbed in concentrated H2SO4 to produce oleum. Dilution of oleum with water gives H2SO4 of the desired concentration. In the industry, two steps are carried out simultaneously to make the process a continuous one and also to reduce the cost. SO3 plus sulfuric acid will give oleum H2S2O7. The sulfuric acid obtained by contact process is 96 to 98% pure. So here you can look at the diagram, the flow diagram for the manufacture of sulfuric acid, and you can get an idea. Properties. Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 and at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with evolution of a large quantity of heat. Hence, care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly into water with constant stirring. The chemical reaction of sulfuric acid are as a result of the following characteristic. A. Low volatility, strong acidic character, strong affinity for water, and ability to act as an oxidizing agent. In aqueous solution, sulfuric acid ionizes in two steps. आप सबको पता है क्या होता है H2SO4 पहले HSO4 माइनस बनता है एंड देन वही HSO4 माइनस क्या बनता है SO42 माइनस. Okay, the larger value of Ka1 is greater than 10 means that H2SO4 is largely dissociated into H plus and HSO4 minus. Greater the value of dissociation constant Ka, the stronger is the acid. तो Ka high, तो acid भी क्या strong. The acid form two series of salts, normal sulfates such as sodium sulfate and copper sulfate, and acid sulfates, example sodium hydrogen sulfate. Sulfuric acid, because of its low volatility, can be used to manufacture more volatile acids from their corresponding salts. Mx plus H2SO4 gives Hx plus M2SO4. X can be fluorine, chlorine, NO3. Concentrated sulfuric acid is a strong dehydrating agent. Many wet gases can be dried by passing through sulfuric acid, provided the gas do not react with acid. Sulfuric acid removes water from organic compounds. It is evident by its charring action on carbohydrates. C12 H22O11 in presence of H2SO4 will give 12 carbon plus water released. Hot concentrated sulfuric acid is a moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acids. Both metals and nonmetals are oxidized by concentrated sulfuric acid, which is reduced to SO2. Copper plus 2H2SO4 will give copper sulfate plus SO2 plus water. Sulfur plus H2SO4 gives SO2 plus water. Carbon with H2SO4 will give carbon dioxide plus sulfur oxide and plus water. Uses. Sulfuric acid is a very important industrial chemical. A nation's industrial strength can be judged by the quantity of sulfuric acid it produces and consumes. It is needed for the manufacture of hundreds of other compounds and also in many industrial processes. The bulk of sulfuric acid produced is used in the manufacture of fertilizers, example ammonium sulfate, superphosphate. Other uses are in petroleum refining, manufacture of pigments, paints, and dye stuff. Intermediates. Detergent industry, metallurgical application, example cleansing metals before enameling, electroplating, and galvanizing. Storage batteries in the manufacture of nitrocellulose product and as a laboratory reagent. Example 7.13. What happens when concentrated sulfuric acid is added to calcium fluoride? When SO3 is passed through water? First, it forms hydrogen fluoride. Calcium CaF2 कैल्शियम फ्लोराइड जब क्या होगा रिएक्ट करेगा सल्फ्यूरिक एसिड से तो कैल्शियम सल्फेट बनेगा दैट इज CaSO4 and hydrogen fluoride HF will get formed. When SO3 is passed through water तो सिंपल है भाई SO3 plus H2O क्या बना लेगा H2SO4. Group 17 elements fluorine, chlorine, bromine, iodine, astatine and tennessine are the members of group 17. These are collectively known as halogens. Greek halo means salt and gens means bond, that is salt producers. The halogens are highly reactive non-metallic elements like groups 1 and 2. The element of group 17 show great similarity amongst themselves. That much similarity is not found in the elements of other group of the periodic table. Also, there is a regular gradation in their physical and chemical properties. Astatine and tennessine are radioactive elements. Occurrence. Fluorine and chlorine are fairly abundant while bromine and iodine less so. Fluorine is present mainly as insoluble fluorides. Fluorspar, CF2, cryolite, Na3AlF6 and fluorapatite 3Ca3 PO4 the whole twice dot CaF2 and small quantities are present in soil, river water plants and bones and teeth of animal. Seawater contains chlorides, bromides and iodides of sodium, potassium, magnesium and calcium but is mainly sodium chloride solution 2.5% by mass. The deposits of dried up seas contain these compounds. Example sodium chloride and carnallite. Carnallite KCl.MgCl2.6H2O. Double salt बोलते हैं ना. Certain forms of marine life contain iodine in their systems. Various seaweeds, for example, contain up to 0.5% of iodine and Chile saltpeter contains about 0.2% of sodium iodate. Here, important atomic and physical properties of group 17 elements other than tennessine are given along with their electronic configuration in table 7.8. Tennessine is a synthetic radioactive element. Its symbol is Ts, atomic number is 117, atomic mass is 294 and electronic configuration is Rn 5f14, 6d10, 7s2, 7p5. Only very small amount of the element could be prepared. Also its half-life is in milliseconds only. That is why its chemistry could not be established. So here you can look at the table where it shows the atomic and physical properties of fluorine, chlorine, bromine, iodine and astatine. I have no such mnemonic for these elements because I it is directly memorizable. Okay. The trends of some of the atomic, physical, and chemical properties are discussed below. Electronic configuration. All these elements have seen electrons in their outermost shell, Ns2np5, which is one electron short of the next noble gas. Atomic and ionic radii. The halogen have the smallest atomic radii in their respective periods due to maximum effective nuclear charge. The atomic radius of fluorine, like the other elements of the second period, is extremely small. Atomic and ionic radii increase from fluorine to iodine due to increasing number of quantum shells. Ionization enthalpy, they have little tendency to lose electron. Thus, they have very high ionization enthalpy. Due to increase in atomic size, ionization enthalpy decreases down the group. Electron gain enthalpy. Halogens have maximum negative electron gain enthalpy in the corresponding periods. This is due to the fact that the atoms of these elements have only one electron less than stable noble gas configuration. Electron gain enthalpy of the elements of the group becomes less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to small size of fluorine atom. As a result, there are strong inter-electronic repulsions in the relatively small 2p orbitals of fluorine, and thus the incoming electron does not experience much attraction. Electronegativity. Negativity. They have very high electronegativity. The electronegativity decreases down the group. Fluorine is the most electronegative element in the periodic table. Example 7.14. Halogens have maximum negative electron gain enthalpy in the respective periods of the periodic table. Why? The answer is halogen have the smallest size in their respective period and therefore high effective nuclear charge. As a consequence, they readily accept one electron to acquire noble gas electronic configuration. Physical properties. Halogens display smooth variation in their physical properties. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid. Their melting and boiling points steadily increase with atomic number. All halogens are colored. This is due to absorption of radiation in visible region, which results in the excitation of outer electrons to higher energy level. By absorbing different quanta of radiation, they display different colors. For example, F2 has yellow, Cl2 greenish yellow, Br2 red, and I2 violet color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons to give colored solution. One curious anomaly we notice from table 7.8 is the smaller enthalpy of dissociation of F2 compared to that of Cl2, whereas XX bond dissociation enthalpy from chlorine onwards show the expected trend. Chlorine chlorine, then bromine bromine, देन आयोडीन आयोडीन. मतलब क्या बोलना चाह रहे हैं कि जो अगर आप क्लोरीन क्लोरीन बॉन्ड को डिसोसिएट करोगे तोड़ोगे तो उसमें सबसे ज़्यादा एनर्जी लगेगी. देन ब्रोमीन ब्रोमीन एंड देन आयोडीन आयोडीन. A reason for this anomaly is the relatively large electron-electron repulsion among the lone pairs in F2 molecule, where they are much closer to each other than in case of Cl2. तो bond dissociation अगर आप करने जाओगे F2 and Cl2 में तो Cl2 F2 का क्या हो जाएगा, इट विल इजीली डिसोसिएट. क्यों? क्योंकि ऑलरेडी देर इज वेरी हाई इलेक्ट्रॉन क्लाउड ओवर देयर एंड सो ऑलरेडी देर इज रिपल्शन. तो वो लोग बोलते हैं कि ठीक है हम अलग ही हो जाते हैं. तो F2 बॉन्ड को ब्रेक करना, दैट इज फ्लोरीन फ्लोरीन बॉन्ड को ब्रेक करना इजी है एज कंपेयर टू क्लोरीन क्लोरीन बॉन्ड को ब्रेक करना. Example 7.15. Although electron gain enthalpy of fluorine is less negative as compared to chlorine, fluorine is a stronger oxidizing agent than chlorine. Why? The answer is it is due to low enthalpy of dissociation of fluorine-fluorine bond. Second, high hydration enthalpy of F minus. Chemical properties. Oxidation states and trends in chemical reactivity. All halogen exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit +1, +3, +5 and +7 oxidation state also as explained below. So here you can see halogen atom in ground state other than fluorine. It is NS2 NP5 and their ND is vacant. यहाँ फ्लोरीन की बात नहीं हो रही है, ठीक है. तो फर्स्ट एक्साइटेड स्टेट वुड बी P से इलेक्ट्रॉन जंप करके जाएगा D में. सेकेंड एक्साइटेड स्टेट में भी P से इलेक्ट्रॉन जंप करके जाएगा D में. एंड थर्ड एक्साइटेड स्टेट में क्या हो जाएगा, NS का जो पेयर्ड इलेक्ट्रॉन है वहां से इलेक्ट्रॉन जंप करके जाएगा D में. तो यर एज यू मूव तो +1 ऑक्सीडेशन स्टेट देखने मिल सकता है, -1 भी देखने मिल सकता है. 3 है तो +3, +5 and +7 oxidation state can also be seen. The higher oxidation state of chlorine, bromine and iodine are realized mainly when the halogens are in combination with the small and highly electronegative fluorine and oxygen atoms. Example in interhalogen oxides and oxoacids. The oxidation states of +4 and +6 occur in oxides and oxoacids of chlorine and bromine. The fluorine atom has no d orbital in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with metals and nonmetals to form halides. The reactivity of the halogen decreases down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogen F2 of the halogens. F2 is the strongest oxidizing halogen and it oxidizes other halide ions in the solution or even in solid phase. In general, a halogen oxidizes halide ions of higher atomic number. So F2 2x minus, this x can be chlorine, bromine or iodine. तो क्या हो जाएगा 2f minus and x2 will be released. ठीक है, तो ऑक्सीडेशन हो रहा है of the higher halide. The decreasing oxidizing ability of the halogens in aqueous solution down the group is evident from their standard electrode potential, table 7.8, which are dependent on the parameters indicated below. The relative oxidizing power of halogen can further be illustrated by their reactions with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acid. The reaction of iodine with water is non-spontaneous. In fact, I- can be oxidized by oxygen in acidic medium. Just the reverse of the reaction observed with fluorine. ठीक है, तो फ्लोरीन जब रिएक्ट करता है वाटर से तो आपको ऑक्सीजन रिलीज होता हुआ दिखाई देगा. जब क्लोरीन ब्रोमीन वाटर से रिएक्ट करेंगे तो हाइड्रोहेलिक या फिर हाइपोहेलस एसिड देखने मिलेगा. लेकिन आयोडीन के केस में ऐसा नहीं है. आयोडीन क्या है, आयोडीन रिएक्ट ही नहीं करता है वाटर से. उल्टा what will happen if there is I minus, it will react with oxygen to give iodine molecule and water. उल्टा ऑफ द फ्लोरीन का जो रिएक्शन हमने देखा. Okay, anomalous behavior of fluorine. Like other elements of P block present in the second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity, and electrode potential are all higher for fluorine than expected from the trends set by other halogens. Also, ionic and covalent radii, melting point and boiling point, enthalpy of bond dissociation, and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, highest electronegativity, low fluorine fluorine bond, dissociation enthalpy, and non availability of d orbitals in its valence shell. Most of the reactions of fluorine are exothermic due to small and strong bond formed by it with other elements. It forms only one oxoacid while other halogens form a number of oxoacids. Hydrogen fluoride is a liquid, boiling point 293 Kelvin. Due to strong hydrogen bonding, hydrogen bond is formed in HF due to small size and high electronegativity of fluorine. Other hydrogen halides which have bigger size and less electronegativity are gases. Reactivity towards hydrogen. They all react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. Hydrogen halides dissolve in water to form hydrohalic acid. Some of the properties of hydrogen halides are given in the table 7.9. The acidic strength of these acids varies in the order HF less than HCl less than HBr less than HI. मतलब HI क्या है? It has the greatest acidic strength. The stability of these halides decrease down the group due to decrease in bond HX dissociation enthalpy in the order HF very high, then HCl, then HBr and then HI. मतलब HF क्या है? It is the greatest, it is most stable and HI being the least stable. Here you can in the table you can see the properties of hydrogen halide. Melting point, boiling point देख सकते हो, bond length को compare कर सकते हो, and on that basis you can understand कि क्यों stable है और क्यों unstable है. Reactivity towards oxygen. Halogen form many oxides with oxygen, but most of them are unstable. Fluorine form two oxides, OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluorides because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to PuF6 and the reaction is used in removing plutonium as PuF6 from spent nuclear fuel. Chlorine, bromine and iodine form oxides in which oxidation state of these halogen range from +1 to +7. A combination of kinetic and thermodynamic factors lead to the generally decreasing order of the stability of oxides formed by halogens. I is greater than chlorine and then bromine. Higher stability of oxides of iodine is due to greater polarizability of bond between iodine and oxygen. In case of chlorine, multiple bond formation between chlorine and oxygen takes place due to availability of d orbitals. This leads to increase in stability. Bromine lacks both the characteristic, hence stability of oxides of bromine is least. The higher oxides of halogens tend to be more stable than the lower ones. Chlorine oxides Cl2O, ClO2, Cl2O6 and Cl2O7 are highly reactive oxidizing agent and tend to explode. ClO2 is used as a bleaching agent for paper pulp and textiles in water treatment. The bromine oxides Br2O, BrO2, BrO3 are the least stable halogen oxides, middle row anomaly, and exist only at low temperature. They are very powerful oxidizing agent. The iodine oxides I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in the estimation of carbon monoxide. Reactivity towards metals. Halogen reacts with metal to form metal halides. For example, bromine reacts with magnesium to give magnesium bromide. Magnesium reacts with bromine to give magnesium bromide. The ionic character of the halides decreases in the order MF, MCl, MBr and Mi. So that is, metal fluorides are the strongest and metal iodide is the lowest. Okay, so ionic character of metal fluoride is more as compared to metal iodide, where M is a monovalent metal. If a metal exhibits more than one oxidation state, the halides in the higher oxidation state will be more covalent than the one in the lower oxidation state. For example, SnCl4, PbCl4, SbCl5 and UF6 are more covalent than SnCl2, PbCl2, SbCl3 and UF4 respectively. Reactivity of halogens towards other halogens. Halogens combine amongst themselves to form a number of compounds known as interhalogens of the types XX-, XX3-, XX5 and XX7, where X is the larger size halogen and X is smaller size, X- is the smallest size halogen. Example 7.16. Fluorine exhibits only -1 oxidation state, whereas other halogen exhibit +1, +3, +5 and +7 oxidation states also. Explain. The solution is simple. See, fluorine is the most electronegative element and cannot exhibit any positive oxidation state. Other halogens have d orbitals and therefore can expand their octets and show +1, +3, +5 and +7 oxidation states also. Chlorine. Chlorine was discovered in 1774 by Scheele by the action of hydrochloric acid on MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. Chloris means greenish yellow. Preparation. It can be prepared by any one of the following methods. By heating manganese dioxide with concentrated hydrochloric acid, MnO2 plus 4HCl will give MnCl2 plus Cl2 plus 2H2. However, a mixture of common salt and concentrated sulfuric acid is used in place of HCl. By the action of HCl on potassium permanganate. So these are the preparation methods. ठीक है, पहले तो मैंगनीज डाइऑक्साइड से, फिर कोई कॉमन सॉल्ट से ले लो, तो NaCl लिया है हमने, एंड बाय द एक्शन ऑफ HCl ऑन पोटेशियम परमैंगनेट. ये सारे क्या करेंगे, आपको क्लोरीन प्रिपेयर करके दे देंगे. Manufacture of chlorine. Decon's process. By oxidation of hydrogen chloride gas, by atmospheric oxygen in the presence of CuCl2 catalyst at 723 Kelvin. So 4HCl plus O2 and cupric chloride will give Cl2 plus 2H2O. Electrolytic process. Chlorine is obtained by electrolysis of brine, concentrated NaCl solution. Chlorine is liberated at the anode. It is also obtained as a byproduct in many chemical industries. Properties. It is a greenish yellow gas with pungent and suffocating odor. It is about 2-5 times heavier than air. It can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. It is soluble in water. Chlorine reacts with a number of metals and non-metals to form chlorides. तो metals के साथ react करेगा. If it is reacting with sodium, तो sodium chloride बन जाएगा. If it is reacting with aluminium, तो aluminium chloride बन जाएगा AlCl3. आयरन के साथ react कर रहा है तो FeCl3 बन जाएगा. अगर नॉन मेटल्स के साथ रिएक्ट कर रहा है, फॉस्फोरस, तो फॉस्फोरस PCl3, एसिड दैट इज सल्फर के साथ रिएक्ट कर रहा है तो S2Cl2. It has great affinity for hydrogen. It reacts with compounds containing hydrogen to form HCl. हाइड्रोजन एंड क्लोरीन को मिक्स करो, HCl बन जाएगा. हाइड्रोजन सल्फाइड और क्लोरीन को मिक्स करो तो HCl बन जाएगा, सल्फर रिलीज होगा. C10H16 प्लस क्लोरीन मिक्स करो तो वापस से HCl बन जाएगा और कार्बन रिलीज हो जाएगा. With cold and dilute alkalis, chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkalis, it gives chloride and chlorate. ठीक है. With cold and dilute alkalis, chlorine produces a mixture of chloride and hypochlorite, but with hot concentrated alkalis, it gives chloride and chlorate. ठीक है. NaOH के साथ रिएक्ट करेगा तो क्लोराइड दैट इज सोडियम क्लोराइड बना एंड सोडियम हाइपोक्लोराइड बना व्हेन इट वाज डाइल्यूट. जब कॉन्सेंट्रेटेड हो जाएगा तो क्या बन जाएगा, सोडियम क्लोराइड एंड सोडियम क्लोरेट. ठीक है. दिस इज द डिफरेंस. कोल्ड में सोडियम क्लोराइड एंड सोडियम हाइपोक्लोराइड, वही चीज हॉट एंड कॉन्सेंट्रेटेड है तो सोडियम क्लोराइड एंड सोडियम क्लोरेट. Okay, with dry slake lime it gives bleaching powder. तो bleaching powder कैसे बनता है, it is very important. Slake lime that is calcium hydroxide, क्लोरीन में मिक्स किया तो calcium oxychloride बनता है जिसको ही हम बोलते हैं bleaching powder. Okay, the composition of bleaching powder is calcium in bracket OCl2 OCl twice dot CaCl2 dot CaOH twice dot 2H2O. Chlorine reacts with hydrocarbons and give substitution products with saturated hydrocarbons and addition products with unsaturated hydrocarbons. सिंपल, आपको तो पता होगा. मीथेन के साथ रिएक्ट करेगा तो मिथाइल क्लोराइड देगा एंड इथीन के साथ रिएक्ट करेगा तो क्या होगा, जेमिनाइल प्रोडक्ट्स मिलता है हमें 1,2-dichloroethane. Chlorine water on standing loses its yellow color due to formation of HCl and HOCl, that is hypochlorous acid. So formed gives nascent oxygen which is responsible for oxidizing and bleaching properties of chlorine. Chlorine oxidizes ferrous to ferric and sulfite to sulfate. Chlorine oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In the presence of water, they form sulfuric acid and iodic acid respectively. So here there are some reactions given. You can look at the screen, pause the video and go through it. Chlorine is a powerful bleaching agent. Bleaching action is due to oxidation. It bleaches vegetable or organic matter in the presence of moisture. Bleaching effect of chlorine is permanent. Cl2.H2O gives 2HCl plus nascent oxygen. Colored substance plus oxygen gives colorless substance. Uses. It is used for bleaching wood pulp required for manufacture of paper and rayon, bleaching cotton and textiles, in the extraction of gold and platinum, in the manufacture of dyes, drugs and organic compounds such as carbon tetrachloride, chloroform, DDT, refrigerants, etc. In sterilizing drinking water and preparation of poisonous gases such as phosgene, that is COCl2, tear gas, CCl3NO2, mustard gas, Cl, CH2CH2, sulfur, CH2CH2Cl. Example 7.17. Write the balanced chemical equation for the reaction of chlorine with hot and concentrated NaOH. Is this reaction a disproportionation reaction? Justify. 3 chlorine with 6 NaOH concentrated. याद है हमने concentrated में बात की थी कि क्या बनेगा, सोडियम क्लोराइड एंड NaClO3 क्लोरेट्स बनाता, right? Plus 3H2O. Yes, chlorine from 0 oxidation state is changed to -1 and +5 oxidation state. तो reduction भी हुआ है and oxidation भी हुआ है. So hence it is a disproportionation reaction. Hydrogen chloride. Glauber prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davy in 1810 showed that it is a compound of hydrogen and chlorine. Preparation. In laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. NaCl plus H2SO4 क्या मिलेगा? पहले तो HCl जो चाहिए हमें एंड NaHSO4. NaHSO4 को वापस अगर सॉल्ट से मिक्स करोगे और हीट करोगे तो क्या मिलेगा? सोडियम सल्फेट निकल जाएगा एंड वापस से HCl विल बी obtained. HCl gas can be dried by passing through concentrated sulfuric acid. Properties. It is a colorless and pungent smelling gas. It is easily liquefied to a colorless liquid, boiling point 189 Kelvin and freezes to a white crystalline solid, freezing point 159 Kelvin. It is extremely soluble in water and ionizes as follows. HCl reacts with water to give H3O positive plus Cl minus. Ka is 10 raised to 7. Its aqueous solution is called hydrochloric acid. High value of dissociation constant Ka indicates that it is a strong acid in water. It reacts with ammonia and gives white fumes of ammonium chloride. When 3 parts of concentrated HCl and 1 part of concentrated HNO3 are mixed, aqua regia is formed, which is used for dissolving noble metals, example gold, platinum, etc. ठीक है. HCl हमने ऑर्गेनिक में पढ़ा होगा ना, HCl एंड HNO3 3:1 के रेशियो में, तो वो उस मिक्सचर को हम क्या बोलते हैं? एक्वा रेजिया. Hydrochloric acid decomposes salts of weaker acids, example carbonates, hydrogen carbonates, sulfides, etc. तो ये जो भी कार्बोनेट्स है, हाइड्रोजन कार्बोनेट्स है, सल्फाइड्स है, अगर HCl के साथ रिएक्ट करेंगे तो हमको उनका क्या मिल जाएगा? सॉल्ट मिल जाएगा. जैसे सोडियम कार्बोनेट HCl से रिएक्ट हुआ तो सोडियम क्लोराइड मिल गया. सोडियम हाइड्रोजन कार्बोनेट रिएक्ट हुआ तो क्या मिल गया? वापस से सोडियम क्लोराइड मिल गया. एंड सोडियम सल्फाइड अगर Na2SO3 रिएक्ट किया तो क्या हो गया? अगेन सोडियम क्लोराइड मिल गया. Uses. It is used in the manufacture of chlorine, ammonium chloride and glucose from cornstarch, for extracting glue from bones and purifying bone black. Third, in medicine and as a laboratory reagent. Example 7.18. When HCl reacts with finely powdered iron, it forms ferrous chloride and not ferric chloride. Why? The answer is its reaction with iron produces H2. Fe plus 2HCl will give FeCl2 and H2. Liberation of hydrogen prevents the formation of ferric chloride. Oxoacids of halogen. Due to high electronegativity and small size, fluorine forms only one oxoacid, HOF, known as fluoric acid or hypofluorous acid. The other halogen forms several oxoacids. Most of them cannot be isolated in pure state. They are stable only in aqueous solution or in the form of their salts. The oxoacids of halogens are given in table 7.10 and their structures are given in figure 7.8. Oxoacids of halogen तो आप लोग को दिख रहा होगा, hypohalous, फिर hypochlorous, hypobromous and hypoiodous. ठीक है, इसमें जो ऑक्सीडेशन स्टेट है वो +1 है. देन हैलस एसिड HOClO क्लोरस एसिड है सिर्फ. देन हैलिक एसिड में क्लोरिक एसिड, ब्रोमिक एसिड, आयोडिक एसिड. एंड पर हैलिक एसिड में पर क्लोरिक एसिड, पर ब्रोमिक एसिड, पर आयोडिक एसिड. सो ऑक्सीडेशन स्टेट 7 तक गया है. हियर यू कैन सी द स्ट्रक्चर. अगेन ऑक्साइड्स, ऑक्सो एसिड्स, ये सब एलिमेंट्स, इनके जो स्ट्रक्चर्स हैं, उनका नाम और उनका मॉलिकुलर फॉर्मूला वो बहुत बहुत इंपॉर्टेंट है. यू सी टू इट दैट कि आप एक पेज बना लो एंड उस पर पूरा नोट कर लो कि ऑक्सो एसिड कौन से है, उनके ऑक्साइड्स क्या है. ये सब बहुत इंपॉर्टेंट हो जाता है एज पर नीट एग्जाम पॉइंट ऑफ व्यू. ठीक है. Interhalogen compounds. When two different halogen reacts with each other, interhalogen compounds are formed. They can be assigned general composition as XX dash, XX3 dash, XX5 dash, and XX7, where X is halogen of larger size and X dash of smaller size, and X is more electropositive than X dash. As the ratio between radii of X and X dash increases, the number of atoms per molecule also increases. Thus, iodine 7 fluoride should have maximum number of atoms, as the ratio of radii between iodine and fluorine should be maximum. That is why its formula is IF7, having maximum number of atoms. Preparation. The interhalogen compounds can be prepared by direct combination or by action of halogen on lower interhalogen compounds. The product formed depends upon some specific condition. तो क्लोरीन फ्लोरीन रिएक्ट करेंगे तो क्या मिल जाएगा? क्लोरीन फ्लोराइड मिल जाएगा. Cl2F2 रिएक्ट करोगे तो Clf3 भी मिल सकता है. I2Cl2 ICl, I2Cl2 ICl3, BrF3, BrF5. तो इस तरह से कॉम्बिनेशन से we can get the interhalogen compounds. Properties. Some properties of interhalogen compounds are given in the table. You can look over here. So ClF is a colorless gas, BrF is pale brown gas. तो इस तरह से पूरा उनका जो फिजिकल स्टेट एंड कलर है. ऑल्सो स्ट्रक्चर, केमिकल बॉन्डिंग पॉइंट ऑफ व्यू से उनके स्ट्रक्चर, इंटर हैलोजन कंपाउंड्स के स्ट्रक्चर बहुत बहुत इंपॉर्टेंट है. ठीक है, तो आप लोग प्लीज चेक कर लेना. इंटर हैलोजन कंपाउंड में कंफ्यूज कर देते हैं एंड पोजीशन भी पूछते हैं कि एक्सियल पोजीशन पे कौन सा है, इक्वेटोरियल पोजीशन पे कौन सा है. तो स्ट्रक्चर एंड शेप, ज्योमेट्री होती है ना, वो बहुत इंपॉर्टेंट है. ठीक है. Okay, these are all covalent molecules and are diamagnetic in nature. They are volatile solids or liquids at 298 Kelvin except ClF, which is a gas. Their physical properties are intermediate between those of constituent halogens except that their melting point and boiling point are a little higher than expected. Their chemical reaction can be compared with the individual halogen. In general, interhalogen compounds are more reactive than halogen except fluorine. This is because X dash X dash bond in interhalogen is weaker than XX bond in halogen except fluorine-fluorine bond. All these undergo hydrolysis giving halide ion derived from the smaller halogen and a hypohalite when XX dash, halite when XX-3, halate when XX-5, and perhalate when XX-7, anion derived from the larger halogen. Their molecular structures are very interesting, which can be explained on the basis of valence shell electron pair repulsion theory, that is VSEPR theory. The XX3 compounds have the bent T shape, XX5 compounds square pyramidal, and IF7 has pentagonal bipyramidal structures. Discuss the molecular shape of BrF3 on the basis of the Vesper theory. The central atom Br has 7 electrons in the valence shell. 3 of these will form electron pair bonds with 3 fluorine atoms, leaving behind 4 electrons. Thus, there are 3 bond pairs and 2 lone pairs. According to Vesper theory, these will occupy the corners of the trigonal bipyramid. The 2 lone pairs will occupy equatorial positions to minimize lone pair and bond pair lone pair repulsions, which are greater than bond pair repulsion. In addition, the axial fluorine atoms will be bent towards the equatorial fluorine in order to minimize the lone pair repulsion. The shape would be that of slightly bent T-shaped. Okay. Uses. The compounds can be used as non-aqueous solvent. Interhalogen compounds are very useful fluorinating agents. ClF3 and BrF3 are used for the production in UF6 in the enrichment of 235U. U in solid state reacts with 3ClF3 to give UF6 plus 3ClF. Group 18 elements. Group 18 consists of elements helium, neon, argon, krypton, xenon, radon, and oganesson. All these are gases and chemically unreactive. They form very few compounds. Because of this, they are termed as noble gases. Occurrence. All these gases except radon and oganesson occur in the atmosphere. Their atmospheric abundance in dry air is almost 1% by volume, of which argon is the major constituent. Helium and sometimes neon are found in minerals of radioactive origin. Example, pitchblende, monazite, clevite. The main commercial source of helium is natural gas. Xenon and radon are the rarest element of the group. Radon is obtained as a decay product of 226 radon. 22688 radon gives 222 radon, 226 Rn, 86 plus 4 by 2 helium. Oganesson has been synthetically produced by collision of 24998 CF atoms and 4820 calcium ions. ठीक है, atomic number is 48 and the atomic mass is 48 and atomic number is 20. इस तरह से oganesson को बनाया गया है. Okay, and when oganesson is produced, 3N are released. Example 7.20. Why are the elements of group 18 known as noble gases? The elements present in group 18 have their valence shell orbitals completely filled and therefore react with a few elements only under certain conditions. Therefore, they are known as noble gases. Oganesson has its symbol Og, atomic number 118, atomic mass 294 and electronic configuration Rn 5f14 6d10 7s2 7p6. Only very small amount of oganesson has been produced. Its half-life is 0.7 milliseconds. Therefore, mainly prediction about its chemistry have been made. Here, except for oganesson, important atomic and physical properties of other elements of group 18 along with their electronic configuration are given in table 7.12. The trends in some of the atomic, physical and chemical properties of the group are discussed here. So you can look at the table, compare things, atomic number, boiling point, melting point, and get an idea of group 18 elements. Electronic configuration. All noble gases have general electronic configuration Ns2 Np6 except helium, which has 1s2. Many of the properties of noble gases, including their inactive nature, are ascribed to their closed shell structures. Ionization enthalpy. Due to stable electronic configuration, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radii increase down the group with increase in atomic number. Electron gain enthalpy. Since noble gas have stable electronic configuration, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpies. Physical properties. All the noble gases are monoatomic. They are colorless, odorless and tasteless. They are sparingly soluble in water. They have very low melting and boiling point because the only type of interatomic interaction in these elements is weak dispersion forces. Helium has the lowest boiling point, 4.2 Kelvin, of any known substance. It has an unusual property of diffusing through most commonly used laboratory materials such as rubber, glass, or plastics. Example 7.21. Noble gases have very low boiling points. Why? Noble gases being monoatomic have no interatomic forces except weak dispersion forces and therefore they are liquefied at very low temperatures, hence they have very low boiling points. Chemical properties. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to the following reason. The noble gas except helium, 1s2, have completely filled Ns2 Np6 electronic configuration in their valence shell. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of noble gases has been investigated occasionally ever since their discovery, but all attempts to force them to react to form the compounds were unsuccessful for quite a few years. In March 1962, Neil Bartlett, then at the University of British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2 plus PTF6 minus. He then realized that the first ionization enthalpy of molecular oxygen, 1175 kilojoule per mole, was almost identical with that of xenon, 1170 kilojoule per mole. He made efforts to prepare same type of compounds with xenon and was successful in preparing another red color compound Xc plus PTF6 minus by mixing PTF6 and xenon. After this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. The compounds of krypton are fewer. Only the difluoride KrF2 has been studied in detail. Compounds of radon have not been isolated but only identified. Example, RnF2 by radiotracer technique. No true compounds of argon, neon, or helium are yet known. Xenon fluorine compounds. Xenon forms three binary fluorides XCF2, XCF4, and XCF6 by the direct reaction of elements under appropriate experimental condition. So when it is xenon in excess and fluorine at 673 Kelvin and 1 bar pressure, XCF2 is formed. Xenon is in 1:5 ratio, then 873 Kelvin and 7 bar, XCF4 is formed. When xenon and fluorine is in 1:20 ratio at lower temperature and higher pressure, then XCF6 is formed. XCF6 can also be prepared by interaction of XCF4 and O2F2 at 143 Kelvin. XCF4 plus O2F2 gives XCF6 plus O2. XCF2, XCF4 and XCF6 are colorless crystalline solids and sublime readily at 298 Kelvin. They are powerful fluorinating agents. They are readily hydrolyzed even by traces of water. For example, XCF2 is hydrolyzed to give Xc, HF and O2. The structures of the three xenon fluorides can be deduced from VSEPR and these are shown in figure 7.9. XCF2 and XCF4 have linear and square planar structures respectively. XCF6 has 7 electron pairs, 6 bonding pairs and 1 lone pair and would thus have a distorted octahedral structure as found experimentally in the gas phase. Xenon fluorides react with fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. So here you can see XCF2 reacts with PF5 to form XCF plus and PF6 minus. Okay, so you can look at the reaction over there. Xenon oxygen compounds. Hydrolysis of XCF4 and XCF6 with water gives XCO3. Partial hydrolysis of XCF6 gives oxyfluorides XCOF4 and XCO2F2. XCO3 is a colorless explosive solid and has a pyramidal molecular structure. XCOF4 is a colorless volatile liquid and has a square pyramidal molecular structure. Example 7.22. Does the hydrolysis of XCF6 lead to a redox reaction? No. The products of hydrolysis are XCOF4 and XeO2F2, where the oxidation states of all the elements remain the same as it was in the reacting state. So, therefore, it is not a redox reaction. Uses: helium is a non inflammable and light gas, hence, it is used in filling balloons for meteorological observation. It is also used in gas cooled nuclear reactors. Liquid helium, boiling point 4.2 Kelvin, find use as a cryogenic agent for carrying out various experiments at low temperature. It is used to produce and sustain powerful superconducting magnets, which form an essential part of modern NMR spectrometers and magnetic resonance imaging (MRI) system for clinical diagnosis. It is used as a diluent for oxygen in modern diving apparatus because of its very low solubility in blood. Neon is used in discharge tubes and fluorescent bulbs for advertisement display purposes. Neon bulbs are used in botanical gardens and in greenhouses. Argon is used mainly to provide an inert atmosphere in high temperature metallurgical processes, arc welding of metals or alloys, and for filling electrical bulbs. It is also used in the laboratory for handling substances that are air sensitive. There are no significant uses of xenon and krypton. They are used in light bulb designed for special purposes. Summary: Group 13 to 18 of the periodic table consist of p block elements with their valence shell electronic configuration ns2 np1 से 6 तक. Group 13 and 14 were dealt with in class 11th. In this unit, remaining groups of p block have been discussed. Group 15 elements consist of 5 elements, namely nitrogen, phosphorus, arsenic, antimony, and bismuth, which have general electronic configuration ns2 np3. Nitrogen differs from other elements of this group due to small size, formation of p-pi multiple bond with itself and with high electronegative atom like oxygen or carbon, and non-availability of d orbitals to expand its valence shell. Elements of group 15 show gradation in properties. They react with oxygen, hydrogen, and halogen. They exhibit two important oxidation states, +3 and +5. +3 oxidation is favored by heavier elements due to inert pair effect. Dinitrogen can be prepared in laboratory as well as on industrial scale. It forms oxide in various oxidation state as N2O, NO, N2O3, NO2, N2O4 and N2O5. These oxides have resonating structures and have multiple bonds. Ammonia can be prepared on a large scale by Haber's process. HNO3 is an important industrial chemical. It is a strong monobasic acid and is a powerful oxidizing agent. Metals and nonmetals react with HNO3 under different conditions to give NO or NO2. Phosphorus exists as P4 in elemental form. It exists in several allotropic forms. It forms hydride PH3, which is highly poisonous gas. It forms two types of halides as PX3 and PX5. PCl3 is prepared by the reaction of white phosphorus with dry chlorine, while PCl5 is prepared by the reaction of phosphorus with SO2Cl2. Phosphorus forms a number of oxoacids depending upon the number of POH groups. Their basicity varies. The oxoacid which have pH bonds are good reducing agent. Group 16 elements have general electronic configuration NH2NP4. They show maximum oxidation state +6. Gradation in physical and chemical properties is observed in group 16 element. In laboratory, dioxygen is prepared by heating KClO3 in presence of MnO2. It forms a number of oxides with metals. Allotropic forms of oxygen is O3, which is highly oxidizing agent. Sulfur forms a number of allotropes. Of these, alpha and beta form of sulfur are most important. Sulfur combines with oxygen to give oxides such as SO2 and SO3. SO2 is prepared by direct union of sulfur with oxygen. SO2 is used in manufacture of sulfuric acid. Sulfur forms a number of oxo acids. Amongst them, the most important is H2SO4. It is prepared by contact process. It is a dehydrating and oxidizing agent. It is used in manufacture of several compounds. Group 17 of the periodic table consists of the following elements: fluorine, chlorine, bromine, iodine, and astatine. These elements are extremely reactive and as such they are found in the combined state only. The common oxidation state of these elements is -1. However, higher oxidation state can be +7. They show regular gradation in physical and chemical properties. They form oxides, hydrogen halides, interhalogen compounds, and oxoacid. Chlorine is conveniently obtained by the reaction of HCl with KMnO4. HCl is prepared by heating NaCl with concentrated H2SO4. Halogens combine with one another to form interhalogen compounds of the type XX-N, where N can be 1, 3, 5, 7, where X dash is lighter than X. A number of oxoacid of halogens are known. In the structure of these oxoacid, halogen is the central atom which is bonded in each case with one OH bond as XOH. In some cases, X is equal to 0 bonds are also found. X double bond oxygen bonds are also found. Group 18 of the periodic table consists of the noble gases. They have NS2, NP6 valence shell electronic configuration except helium, which is 1s2. All the gases except Rn occur in atmosphere. Radon is obtained as the decay product of radium. Due to complete octet of outermost shell, they have less tendency to form compounds. The best characterized compounds are those of xenon with fluorine and oxygen only under certain conditions. These gases have several uses. Argon is used to provide inert atmosphere. Helium is used in filling balloons for meteorological observation. Neon is used in discharge tube and fluorescent bulbs. So here we complete the entire P block elements. I hope you all enjoyed listening to the audio. So please hit the like button, subscribe to the channel, and thank you so much for watching. Keep studying. Bye bye. Have a great day.